Today we are going to look at the next topic in our module 3. RSA എന്ന് പറയുന്നത് most probably one of the most popular public key crypto systems. It is one of the first also which was used for secure crypto systems over the net. Okay, now as usual before we go for the actual algorithm, നമുക്ക് ആവശ്യമായ ചില മാത്തമാറ്റിക്സ് ഉണ്ട്. ഹിയർ വാട്ട് യു റിക്വയർ ഇസ് മോഡ്യുലർ അരിത്മെറ്റിക്. ഗലോവ ഫീൽഡ് ഓൾറെഡി നമ്മൾ നോക്കിയതാണ്. ഓർമ്മയില്ലെങ്കിൽ ഒന്നുകൂടെ ചെന്ന് നോക്കുക. അതിൻ്റെ കൂടെ തന്നെ മോഡ്യുലർ അരിത്മെറ്റിക്കും കൂടെ നമുക്കിവിടെ ആവശ്യമുണ്ട്. ഓക്കെ, സോ സിൻസ് ഓൾ ദീസ് തിങ്സ് യു ഹാവ് ഓൾറെഡി സ്റ്റഡീഡ് ഇൻ ദ മാത്സ് ഫോർ സെക്യൂരിറ്റി മാത്തമാറ്റിക്സ് ഇൻ യുവർ ഫസ്റ്റ് പേപ്പർ, I don't want to spend time on it, but if you need to refresh, please go through this YouTube video. I will put the link in the description box. So let's continue. First, an introduction. RSA is short form for the names of the inventors of this particular crypto system. Okay, so Rivest, Sharma and Adelman of MIT, Massachusetts Institute of Technology. In 1977, they invented or designed this particular crypto system. Okay, as I told you earlier, it's probably the most widely used public key scheme. Okay, and the math that is required is one, of course, we require modular arithmetic and then we require Galois fields. Okay, over integers. Okay, so here exponentiation is one of the operations that is going to be done. We are going to discuss more in detail how fast exponentiations can be done, and the exponentiation that is used takes order of log n to the power 3. Okay, order of log n to the power 3. And RSA uses large integers, so around 1024 bits will be the n. Okay, I'm going to show you the algorithm. I'm not talking about the relative primes which are taken. I'm talking about n, which is the multiplication of the two relative primes which will be taken, which you will see in a bit. Okay, so n is equal to 1024 bits, and the security, that is the cost of factoring large numbers, because factorization is a hard problem, security is there in RSA, not because RSA is complicated. Okay, because factorizing large numbers takes order of e raised to log n, log of log n, which is infeasible, or not that it is not possible, it is just not practical. Okay, so it's a hard problem. Now we are going to look at the actual RSA algorithm. RSA algorithm, just like all others, first we need to, we have already looked at what is public key crypto system. We know from that you require two keys, a public key and a private key. Okay, the key generation is the first step. Each step, I'm giving you the overall idea right now, and then we will look at each of the three steps separately, okay, with examples. Key generation, first there is a public key which is equal to e comma n. E is the encryption key, and n, as I told you earlier, is a number which is which is the multiplication of the two primes which are used in getting this n. We will look at the algorithm. And private key is d comma n. As we know, the public key is known publicly, so the value of e and n will be known publicly, and any attacker can get these two values. The thing is that to factorize, to get p and q, you need to factorize this n, and that is not an easy task. As I told you earlier in the previous slide, it takes order of e raised to log n, log of log n, which is a hard problem. Okay, so actually only this d, the decryption key or the private key d, is actually a secret. Everything else is publicly known. Once we have e and d, then a message M is encrypted by doing M raised to E mod n, and the decryption is done by doing the ciphertext C raised to D mod n. Now C raised to D mod n means C raised to D mod n is C. Okay, the C is M raised to E mod n. So C M raised to E mod n raised to D mod n. Okay, so with the rules of exponentiation, we know that it will be equal to M raised to E raised to D, which is equal to M raised to ED mod n. Okay, so these two are very simple. The encryption algorithm, encryption formula and the decryption formula is very simple. Okay, here the only thing required is, because the E and D will be large numbers, exponentiation should be fast, which we are going to look how it is done. Both the sender and the receiver will have N, and the sender will have the public encryption key and only the receiver will have D. Okay. Now, the first step you saw over here, our first step was generating the public and private key. So we are going to look at how the key is set up. Okay. So each user, so if we are part of the public key crypto system, we are the one who generates the public and private key pair. Okay. So the first thing to be done is select two large primes at random, P and Q. Okay. Now, not just large primes, they should be relative primes. Okay. So they should be relative primes, prime to each other. Okay. So P comma Q is selected, two large primes, where in RSA P must be greater than or equal, the size of P and Q must be greater than or equal to 512 bits. Okay, and then when you can see 512 bits into 512 bits will be 1024 bits. Okay, so N is equal to P into Q. Then once these two primes are selected, then N will be calculated, which is P into Q, and phi of N is calculated. We saw the theorem in the video which I had shared for PKC mathematics. Phi of N is calculated as P minus 1 into Q minus 1. Okay. Once these calculations are done, remember that the phi of N is used as the mod of phi of N. Mod of phi of N is used for the key generation setup, whereas for the actual encryption and decryption, mod of N is used, not mod of phi of N. Okay, please remember that. Okay, now once this much is done, P and Q are selected, N is calculated, phi of N is calculated, then at random select the encryption key E, but this E should satisfy these two conditions. E should be in between 1 and phi of N. Okay, in between means it should be less than phi of N. So it should be within phi of N minus 1. Okay, so E should be between these two values, and GCD of E comma phi of N must be equal to 1. GCD of E comma phi of N should be equal to 1. Okay, so only if GCD of E comma phi of N is equal to 1, there will be an inverse for E. I hope you remember the rules. Okay, so these two rules must be satisfied, because D is going to be calculated as the inverse of E. That is why this rule must be satisfied. Okay, so once P and Q are selected, N is calculated, phi of N is calculated, and E is selected at random, a number which is between 1 and phi of N, and which has got an inverse when we do mod phi of N. Okay, then we find the inverse to find the decryption key D. So solve the following equation to find the decryption key D. We know E dot D is equal to 1 mod phi N means D is E dot E raised to minus 1 is equal to 1 mod phi N, if you remember the rules of inverse. Okay, so that means D must be an inverse of E. Okay, so E dot D is equal to 1 mod phi of n, and that D value will be in between 0 and n. Okay, once we have got E and D and we have got n, we simply publish the public encryption key E comma n, and the private decryption key is kept a secret, which is D comma n. Okay, so this is the way in which the key is generated for each user. Once the key is generated, encryption and decryption is quite simple. This is the same key generation algorithm, just written as pseudocode, so you can just go through it. And then for the encryption, if we have a plain text, the requirement is that whatever is n, the message must be less than n. The value of the message must be less than n if we are talking about numerical values. Okay, ciphertext will be equal to m raised to e mod n, and then for decryption we have C as the input, and m will be, the message will be C raised to D mod n. Okay, now to encrypt the message, how it is used, you already know how public key crypto system works, so it's exactly like that. To encrypt a message m, if I want to send it to a particular person, that person's public key is publicly available. So the public key of the recipient is taken and the cipher is calculated and it is sent. When the owner, the recipient, gets the cipher, he simply takes his decryption key, that is the private key, and he does C raised to D mod n, and he computes the original message. Okay, remember this rule: for ciphertext and m to work, the message should be n, must be, because we are doing mod n. Okay, so must be smaller, m must be smaller than modulus of n. Okay, now why RSA works? Here block if needed means in case message is larger, we have to create blocks in such a way that each block is less than modulus n. Okay, now why RSA works? Because of Euler's theorem. We saw this earlier itself. Euler's theorem, a raised to phi n mod n is equal to 1, where GCD of a comma n is equal to 1. This is Euler's theorem. Okay, and in RSA we have n is equal to p comma q, phi is n is equal to p minus 1 into q minus 1, and E and D are chosen in such a way that they are inverse in mod of phi of n. Okay, so E dot D is equal to 1 plus some k into, that is, there is a remainder of 1 with some k into phi of n. Okay, so for when we do to get the original message C raised to D, we have m raised to E dot D, where E dot D is equal to 1 plus k dot phi n. Okay, so it will be, this m raised to E dot D will be equal to m raised to 1 plus k dot phi n. Okay, and all this is mod n, remember that. Okay, so since it is mod n, this particular value will become 1. Okay, m raised to m of phi n will become equal to 1. So then what is left? M raised to 1 into 1 raised to k, which is equal to m. So we get the original message. This is the way in which the proof of RSA is given. Okay, now we are going to look at an example. Remember that the prime numbers that are selected, p and q, must be relatively prime. Okay, so if you take 17 and 11, you should not be able to factorize it further with prime numbers. These two are relative primes. Okay, now once we get two relative primes, n is calculated, p into q, 17 into 11 is equal to 187, and phi of n is calculated, p minus 1 into q minus 1, so it is 16 into 10, which is equal to 160. Okay, then some value is chosen at random, E is chosen at random in such a way that E has got an inverse. Okay, and the value we saw earlier, it should be in between 1 and phi of n minus 1. Okay, so here phi of n minus 1 is going to be, this is phi of n 160, so it's going to be 159. So the value should be between 1 and 159. For easy calculation, we are taking a number which is small enough for us to do calculations. Okay, so E is equal to 7. Check whether it is a like GCD will be equal to 1. How do you check whether GCD will be equal to 1? Check whether when you do find mod of with 160, whether you will get 1 as the result. Okay, when E is equal to, that is, if you find 7 comma 160, you are finding the GCD, you should get 1 as the result. Okay, now for 160, if you do 22 into 7, okay, if you do 22 into 7, you get 154, and the GCD will be equal, just do the in your calculator GCD, or in your scientific calculator, find whether GCD of 7 comma 160 is equal to 1. Okay, and then when you common, the denominator will be, if it is equal to 1, then you can choose 7. Okay, now here it is equal to 1, so it is E is equal to 7, and then we need to find out what is the, to find the private key, we need to find out what is the inverse of 7 mod 160. Okay, so we are finding, when we find the inverse, we find that D is equal to 23 is the inverse of 7. Okay, so you can simply find inverse, also can be found with your calculator, so please do that. 7 into 23 is equal to 161. Okay, so mod 160 means 1 is the remainder, and that D value should also be less than 160. So now we have got both E and we have got D. We have got our private, public key and private key combination, which is equal to public key 7 comma 187 and private key 23 comma 187. Okay, now the first part of our example was generating the key. Now here we have generated the key. Now for a message M is equal to 88, remember that this 88 should be less than the phi of n value. Okay, so the message is less than the phi of n value. So the ciphertext is 88 raised to 7 mod 187, and decryption is 11 raised to 23 mod 187. Okay, so use your modular arithmetic and check that all this is right. Okay, this is another example. The plain text that has been given is 19. The public key is 5 comma 119. So phi of n is 119 and E is equal to 5, and the private key is 77 comma 119. Okay, and then 19 raised to 5 is done over here, and the remainder is 66. So 66 is the ciphertext that is given sent over. 66 raised to 77 will give you the original plain text. This also you can work out and see whether it is right. Okay, now all other things we have looked at. Let's look at how fast X in the thing over here is 19 raised to 5, 66 raised to 77. We have taken small values for E and D, but normally these E and D values will be 512 bits. So how do we do fast exponentiation? That is the question over here, and that is where the implementation of RSA works. Okay, so the method used is square and multiply algorithm. Okay, this algorithm is a very fast and efficient algorithm for exponentiation. The rules are first convert the exponent to bits, okay, to binary bits, and from left to right we have to see that the exponent bits, if they, first we always do squaring of the base number, okay, and then check whether the result has got the exponents in the particular the bits in the particular exponent from left to right, okay. If you encounter a 1, you don't do just a square, you do a square and a multiply. 2 steps will be there, okay, these 2 steps will be there. If it is a 0, then you are going to do only squaring, and we are going to look at examples, okay. And this particular algorithm will only take order of log n. So whatever is the number of bits, only those many steps will be taken to do the exponentiation, okay. Excuse me. 7 raised to 5, we are going to do an example of this square multiply algorithm. 7 raised to 5, the first thing is get the binary of the exponent. So 5 is equal to 101, okay. From now on, whatever all these exponents which you see, they are all binary numbers, they are not decimal numbers, okay. So the first step was, the base is 7, you had to square the 7, okay. Whatever it is, always the first step is square the base, okay. So when you square the base, you have 7 raised to 1 into 7 raised to 1, which is equal to 1 and 1 plus 1 will be 2, and in binary 2 is 10, okay. So you get 710, and if you look over here, the first 2 bits of 5 are 1 and 0, so you don't have to do a multiply here, you already have this correctly, okay. Now use this result and again square. So you have 7 raised to 10 dot 7 raised to 10, which is equal to 10 plus 10, 2 plus 2 is 4, which is equal to 7 raised to 100, okay. But now look at the third bit. The third bit over here is 1. So here we have a square is not enough, we have to do a multiply with the base also. So this result is also multiplied with the base, 7 raised to 1. When you do that, you get 101, and that is the result, okay. So whatever answer you have got over here after this dot product, that is your exponentiation. So 7 raised to 5 we have achieved in just 3 steps, which is the number of bits in the binary 5, okay. Another example, 3 raised to 129, okay. Binary of 129 is 1, 0, 0, 6 zeros and 1. So there are 8 bits, okay. As usual, first we do take the base and multiply it, just square it. Oh, sorry, 1 second. Okay, so you square it and you get 3 raised to 10. Then this number, you can see that the first 2 bits are 10, so there is nothing more to be done. 310 is then taken and squared, so we get 3100. Again you see that this is a 0, so nothing needs to be done. So this is taken and that is squared. Again you do that for the first 7 steps. Okay, after doing it for the first 7 steps, the 8th bit is 1. So there you first do a square, you get 1 and all zeros, but since the 8th bit is 1, you do another step, multiply step, where you do this result is multiplied by the base, and then you get the result. So in 8 steps, 1, 2, 3, 4, 5, 6, 7, 8. In 8 steps, we have got the exponentiation of 3 raised to 129. Okay, so this is the algorithm for the square multiply. This is the code for square multiply algorithm. And now we are going to look at efficient encryption. Okay, encryption uses exponentiation to the power of e. If e is small, this will be faster, but the security will be less. And we already know that we require e, RSA requires e to be at least 512, bits. So often the value that is chosen for E is somewhere like 65537. Okay, if you take E is equal to 3, the attacks are possible, and it will be easy using Chinese remainder theorem or any other theorem to, you know, attack the RSA algorithm. The E is, when E is fixed, we should ensure that, you know, there is a inverse, and P and Q should be relatively prime. Okay, that is, reject any P or Q not relatively prime to E. So whenever you choose the numbers, we should check that it should be P and Q are relative primes. Okay. Then for decryption, again it is an exponentiation, and all the rules for the selecting E is applicable over here also. Larger values of D are required. If we choose E correctly, automatically D will also be fine. Okay. Only the owner of the private key actually knows what this P and Q is. He is the one who has selected the P and the Q. It should be large enough. He is the one who has selected the P and the Q. Okay. Random numbers can also be selected. It can, the algorithm can do it by itself and all those things, but still, unless this P and Q can be factorized from N, it is not possible to break the security of RSA. Okay. So users of RSA determine two relative primes, and E or D are selected, and the inverse is computed for the other. Okay. Primes P and Q should not be easily derived from N. That's why large primes are always used. That means it must be sufficiently large, and typically guess and use probabilistic test is the only thing that can be done to factorize. And guessing is not a big, easy task when the numbers are large. Okay. Exponents E and D are inverses. So to find the inverse, if you remember how we find the inverse, we use extended Euclidean algorithm to compute the inverse. Okay, which we have already seen in the earlier PKC mathematics video. Okay. Now the security. Brute force is one method of attack. Okay. And this is infeasible because of the large size of the numbers. Another method of attack is mathematical attacks, and that is done by factorizing. And since factorizing is a hard problem, it is not possible to do that also. We will look at the different possibilities of mathematical attacks in the next slide. Okay. Then we have timing attacks. That means they try to guess the prime numbers by checking how much time it takes for different messages to be decrypted. That is also, you know, not so easily done, but with sufficient mathematics, it is theoretically possible. Okay. Then chosen ciphertext attacks. That means we can give specific messages and use the ciphertext, getting both the ciphertext to the ciphertext and the message to find out whether you know, the RSA properties can be E and D can be found out. Okay. Now all of these are possible approaches, but none of them have been successfully used. Okay. Now we are looking at the mathematical approaches only. Okay. The factoring problem. Okay. So three approaches to attack RSA mathematically are possible. One is to factor N into P and Q. Okay. So that we can calculate D and E. Once we have got, you know, P and Q, all the other values can be calculated, but the problem is factorization is a hard problem. Then determine phi of n directly without first determine, that is we are guessing. Okay. And if we guess it correctly, then it will allow us to determine D is equal to e raised to minus 1 mod of phi of n. Okay. But again, finding phi of n, guessing it directly also, it is not possible. Then determine D directly without first determining phi of n. Okay. So again here it is a guessing task, and it is not an easy task to do when the numbers are large enough. With this, we are concluding RSA, and in the next class we will do the next public key cryptography. Thank you. Hope you have understood this lesson. For any doubts, please feel free to contact me, and don't forget to like and subscribe.